Welcome back. In this session, we'll continue with the discussion on circular convolution, how to evaluate circular convolution. And in this session, we'll learn how to use DFT to evaluate circular convolution. All right, let's start. So, our goal is to evaluate the circular convolution between two sequences, endpoint circular convolution, and the formula is x1 of n minus k modulo n, x2 of k, or we can also use this expression x1 of k, x2 of n minus k modulo n. So we can give the circular either first sequence or the second sequence. So this is how we can use, how to evaluate the circular convolution. But today what we'll do, we'll evaluate the circular convolution of these two sequences using the DFT. In other words, we'll first obtain y of k. Y of k is the DFT of y of n. That means this is the DFT of the circular convolution between the sequences. See, this becomes equal to the, if you see the derivation of this becomes simply the product of the DFTs of this. So where x1 k is the DFT of x1 of n and x2 of k is the DFT of x2 of n. So what does this say? Our goal is to evaluate y of n, but what we'll do, we'll obtain first y of k. How do we obtain y of k? By taking the multiplication of the DFTs of x1 and then x2 and multiplying those DFTs and getting y of k. Then what we'll do, we'll evaluate y of n by taking the inverse discrete Fourier transform of y of k. Sorry, yes, y of k. Y of k. This is y of, right? Then taking the inverse discrete Fourier transform of this y of k, then we will get y of n. This is the procedure that will be used today. All right. Now, so see again, the beauty of the transform theory is to convert the convolution operation into multiplication operation. Same thing holds true here. It converts the circular operation to a multiplication operation. Only requirement is you need the DFTs of these sequences. You need the DFTs of these sequences, right? So let me illustrate the procedure. Let us follow the same example that we have been following from past few lectures. So let's say x1 of n is 1, 2, 2 and 0, and x2 of n is 0, 1, 2 and 3. So these are the two sequences. Now first, what do I need to evaluate y of k? I need x1k and x2k. Means I need the DFTs of x1 and x2. So x1k is the DFT of x1 of n, and by definition we know the DFT of a sequence is given by this. When n runs from 0 to n minus 1, x1 of n e to the power of minus j 2 pi by m k. And there are several ways to evaluate this. There are several ways to evaluate this, and the one that we'll follow today is the matrix formulation method that we have already derived in the previous session. So we have to evaluate the 4-point DFT. So this will be simply the toroidal factor matrix multiplied by x1 n, and these are arrays. These are the arrays where Wn is a toroidal factor matrix. We already derived for the 4-point. If you remember, this is 1, 1, 1, and 1, 1, 1, 1. Then I believe the values are, if I remember it correctly, minus j, minus 1 j. Please check it. Minus 1, 1, minus 1 j, minus 1, minus j. Then we'll arrange x1n, x1, this will be x10, x11, x12, and x1. So this is how we arrange the terms. Now next what we'll do, we'll substitute the values of x1. So this will be 1, 1, 1 and 1, 1. First column is also 1, minus 1, minus j, this will be minus 1, j, this will be 1, minus 1, minus 1 and 0. Please check the values yourself. So this is 1, 2, 2, and 0. I hope I'm right. Yes, 1, 2, and 2, 0. Multiplying these, what you will get? 1 plus 2 plus 2 is 0. 1 minus 2j minus 2 plus 0. Then it will be 1 minus 2 plus 2 plus 0. Then it will be 1 plus 2j minus 2 plus 0. Please check the terms. So this is 5 minus 1 minus 2j 1 and minus plus 2j. So this is the DFT of the first set. So x1 of k is this. In other words, this is x1 of 0, x1 of 1, x1 of 2, x1 of 3, and the capital X's. So the values if you compare with x1 of 0, x1 of 1, x1 of 2, x1 of 3. So this is the DFT of this sequence. Now we'll evaluate the DFT of the second sequence, means x2 of k, which is same as x2 of 0, x2 of 1, x2 of 2, x2 of 3. So again we will use the matrix formulation since we already computed the total factor matrix. So it will be very simple to use. 1, 1, 1, 1, 1. This is minus j, minus 1 j, minus 1, 1, minus 1. Please check the values itself. So this will be 0, 1, 2, 3. Check the terms. This is 0 plus 2, 1. I think 1, 1, 2 plus 3. Then 0 minus j when you multiply minus 2 plus 3j. We are multiplying the matrices. You know how to do that. Minus 1 plus 2 minus 3. 0 plus j minus 2. So this is our array. And then further simplified. So it will be 6 minus 2 plus 3j minus 2 minus 2 minus 3j. Now one simple way whether you are to check your result whether you are doing it right or wrong. Wherever you have j terms, means the terms which contain j, remember these will be complex conjugate of each other. In 4 point, in 8 point, in 16 point, these will be complex conjugate of j. You can see here we have minus 1 minus 2j. Here you have minus 1 plus 2j. So this is the complex conjugate of this, or this is the complex conjugate of this. Same way here we are computing the 4 point DFT. So minus 2 plus 3j will here we have minus 2 minus 2. Sorry, it is minus 3. So it is minus 3j. This is the complex conjugate of this, or this is the complex conjugate of this. All right. I hope you have got the idea. Means to check your result whether you have done it perform it correct or wrong. Means your calculations are right or wrong. You can just confirm it. These will be the complex conjugate of each other. Now, once you have computed this, what you will do next? What you will do? You will say y of k is simply x1 of k and x2 of k. Right. So multiply the corresponding sample point to get y. Sorry. Using capital for this, so y of 0 will be simply x1 of 0, x2 of 0. So x1 of 0 is 5, x2 of 0 is 6, so this will be 30, right? Then y of 1 will be put k equal 1, x1 of 1, x2 of 1. Multiplying the terms, it will be, I think, minus 1 minus 2j multiplied with minus 2 plus 2j, please check it, and the answer will be, I think, how much is the answer? It will be 6 plus 2j, I think, 6 plus 2j, yes, 6 plus 2j, yes, the answer is 6 plus 2j, please check it. And then y of 2, put k equal to y of, so this will be x1 of 2, x2 of 2. If you multiply the terms corresponding to it is 1 Then y of 3 is x1 of 3, x2 of 3, applying the corresponding terms means 9 plus 2j and minus 2 minus 2j. When you multiply this, it will be 6 minus 2, right? So our y of k is simply, what is y of k? 30 6 plus 2j minus 2, 6 minus 2, right? So this is our r k, but we need y of n. That's our goal is to compute y of n. Now, how we do this? What we can do, we can take the inverse discrete Fourier transform of k. When you do that, you will get y of n. And how do we do this inverse discrete Fourier transform of y of k? There's again several methods. Either you use the formula, that is this formula, y of k e to the power of minus j 2 pi by, and this will be plus this time kn, right? So either you do this, or you can again follow the matrix formulation, and the matrix formulation for this is this y of n, and remember this is complex conjugate of this, and then y of k multiplying with y of k, right? So do that. Let me, this will be 1 by 4 because n is 4. Then the twiddle factor matrix, take the conjugate of that. Now this becomes, we already computed it, you have to replace j by minus j. That's the meaning of complex conjugate. So this will be j now, minus 1 minus j. Please check the terms. I just remember it. This is 1 minus j minus 1 plus j. I hope I have done it right. And substituting y of k that we have just derived. What's y of k? 30, 6 plus 2j minus 2, 6 minus 2j. Right? Compute it. And there is 1 by 4 also here. So then, so this will be 30. This will be 30 plus 6 plus 2j minus 2 plus 6 minus 2j. And the second term will be 30 plus 6j minus 2 plus 2 minus 6j minus 2 minus plus check result myself. Then this will be 30 minus 6 minus 2j minus 2. This will be minus 6 plus 2j. Then the last term will be 30 minus 6j. This will be plus 2. I hope I'm right. Plus 2. And it will be 6j plus 6j. And this will be plus 2. I hope I have done it right. So this will be, have a look at this. Minus 2 and this will be cancelled. This will be 36 minus 2, 34, 40. So I have one more part here. This is 1 by 4. Then this is 40. Then this and this cancels. This and this cancels. This will be, I think, sorry, this will cancel with this, and this is 28. This will not cancel. And I put minus 2 here. So we have minus 2. So it will be 30 minus 2 is minus 28. Now again, you can check this and this will cancel here. This will be minus 12, minus 2 is minus 14, minus 14 and 30 is 16. 16. Please check the terms. Please check the terms yourself. This is 30 plus 36. 36. Let's see the answer in here. Divide every term by 4. This will be 10, 7, 4, and 9. So this is our y of k. So y of this 0. So this is small y of 0. So y of 0, y of 1, y of 2, and y of that means y of 0 is 10, y of 1 is 7, y of 2 is 4, y of 3 is 9. Right? So if you compare the result with the last session, I think these are accurate. Alright, so this is how we use DFT to compare the circular convolution. Now again I will emphasize the result here. Now what we do, y of n, which is the circular convolution between x1 of n and x2 of n. What DFT will do, this will convert the circular convolution between the multiplication of the DFT and the individual sequence. Right? And that's what we exploit to compare the circular convolution. This is very, very important. Alright? Alright, so in the next session what we'll do, we'll see how to evaluate linear convolution using circular convolution. Alright, so we'll see how to evaluate the linear convolution using circular.